In the next 4 lectures, we are going to learn how to calculate the equilibrium concentrations of both reactants and products from a known value of Kc. In a previous lecture, we learned to calculate the value of an equilibrium constant from known initial and equilibrium concentrations. In this lecture, we will investigate a second type of problem, how to determine the equilibrium concentrations of all species given initial concentrations and the equilibrium constant. Note that this type of problem is effectively the reverse of the previous type of problem. In the first type of problem, we do not know the value of Kc, but we can calculate it from the equilibrium concentrations of all reactants, even though we may have to determine these first. In the current problem, we know the value of Kc and the initial concentrations of all species, and we want to calculate the equilibrium concentrations. As before, this second type of problem utilizes the ICE table structure to solve. The process begins in a similar manner. First, once we have read the problem, we fill in as much of the ICE table as we can. Second, at this point, we have to introduce a variable in place of how much each concentration changes. Thirdly, we then determine what the equilibrium concentration should be in terms of the initial concentrations and the variables. Lastly, we substitute the algebraic terms into the equilibrium constant expression and we solve. Let's look at the reaction 2IBr gas going to I2 gas plus Br2 gas. At 150 degrees Celsius, the value of Kp is 8.5 times 10 to the minus 3. If we begin with 0.185 atm of IBr, calculate the partial pressures of all species once the system reaches equilibrium. It is very important through the course of this problem that you pause this video and work the calculations along with me. As before, we begin by building our ICE table for the reaction. Our chemical equation is listed in the top row. We then have our initial, change, and equilibrium rows beneath this. Our first step is, having read the problem, we fill in as much of the ICE table as we can. Returning to the problem, we see that we begin with 0.185 atmospheres of IBr. We add this to our table, and having no information regarding the I2 or the Br2, we can only assume that we begin with 0 of either of these. At this point, to build our change row, we need to introduce a variable in place of how much each concentration or partial pressure changes. It's easiest to always begin with a species that has a coefficient of 1, such as I2 in this example. We don't know how much I2 is being formed, so we need to introduce a variable for that change. Let's call it x. We know that the I2 must increase, and so we put a value of plus x under the I2 column. We then note that for every mole of I2 formed, we also form 1 mole of Br2. This means that the Br2 pressure change will be equal to the pressure change in I2, or plus x. We then note that we consume 2 moles of IBr for every mole of I2 formed. This means that the change in IBr pressure is 2 times the change in pressure for I2. Note that we have to include a negative sign because the partial pressure of IBr is going to decrease through the course of the reaction. Next, we determine what the equilibrium concentrations should be in terms of the initial concentrations and the variables we have introduced. As before, we do this by reading down each column and performing the arithmetic that it states. For IBr, we begin with 0.185 atm, and we decrease by 2x, giving us 0.185 minus 2x. For I2 and Br2, we both begin with 0 atm, and we increase by x. This gives an equilibrium partial pressure of x for each of these. Finally, we can substitute the algebraic terms into the equilibrium constant expression and solve. Our Kp expression has the partial pressure of I2 times the partial pressure of Br2 in the numerator and the partial pressure of IBr squared in the denominator. We know this value is 8.5 times 10 to the minus 3 from the problem. We now substitute in our equilibrium row, and we find that we have x times x in the numerator and 0.185 minus 2x squared in the denominator. Now we can solve for x. Again, I stress that it's very important that you pause this video and work these problems along with me. We begin by squaring out the numerator, and then we FOIL our denominator. Multiplying term by term, we get 0.185 squared, followed by 2x times 0.185 with a negative sign, followed by another 2x times 0.185 with a negative sign, followed by 2x squared. Combining like terms, we find that we have 0.0342 minus 0.740x plus 4x squared now in the denominator. We can now multiply through to clear the denominator. Notice that I have inverted the equation so that the x squared is now on the left-hand side. On the right-hand side, we have 8.5 times 10 to the minus 3 multiplied times our denominator. When we distribute, we find we get 2.9 times 10 to the negative 4 minus 6.3 times 10 to the negative 3 times x plus 0.034 x squared. Lastly, we can move everything over from the right-hand side to the left-hand side. This gives us x squared minus 0.034x squared plus 6.3 times 10 to the minus 3x minus 2.9 times 10 to the negative 4 equals to 0. By combining our x squared terms, we now have our polynomial in standard form. Since we have a second-order polynomial, we can solve using the quadratic formula. Recall that given a quadratic, a times x squared plus b times x plus c equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. From our quadratic, we see that a is equal to 0.966, b is equal to 6.3 times 10 to the negative 3, and c is equal to negative 2.9 times 10 to the negative 4. Do not forget to include the subtraction as a negative sign on c. We can then substitute these values into the quadratic formula. It is important that you work each of these calculations individually. Do not try to type this entire expression into your calculator. It may seem to be faster that way, but you're much more likely to make a mistake. First, we can begin by squaring 6.3 times 10 to the negative 3, yielding 4 times 10 to the negative 5. Then we can multiply 4 times 0.966 times negative 2.9 times 10 to the negative 4, yielding negative 1.1 times 10 to the negative 3. Lastly, we can multiply 2 times 0.966 in the denominator, giving us 1.93. Next, we can subtract under the square root sign. 4 times 10 to the negative 5 minus a negative 1.1 times 10 to the negative 3 gives 1.2 times 10 to the negative 3. At this point, I find it easier to break up our fraction into two individual terms, remembering to include the same denominator on both terms. Note that I first took the square root of 1.2 times 10 to the negative 3, giving 0.034. We can now divide. Negative 6.3 times 10 to the negative 3 divided by 1.93 yields negative 3.26 times 10 to the negative 3. Additionally, 0.034 divided by 1.93 gives 0.0176. As with any quadratic, we have two roots as a solution. The first root is obtained by addition. Negative 3.26 times 10 to the negative 3 plus 0.0176. This gives 0.0144. The second root is obtained by subtraction. Negative 3.26 times 10 to the negative 3 minus 0.0176, giving negative 0.0209. We now have the solution for x, and we can solve for the equilibrium partial pressures. But the first question is, which root do we choose? Because we know that the value of x has to represent a partial pressure and have units of atmospheres, it must also behave physically as a pressure. We know that we are not allowed to have negative pressures, and therefore we can immediately eliminate the negative root. This means that x is equal to 0.0144 atmospheres. We can now use the equilibrium partial pressure row to calculate the equilibrium partial pressures for all three species. We begin with IBR. From the equilibrium partial pressure row, we see that at equilibrium, the partial pressure of IBR is 0.185 atmospheres minus 2 times x, or 2 times 0.0144 atmospheres. This becomes 0.185 atmospheres minus 0.0288 atmospheres, or 0.156 atmospheres. For I2, we see that the equilibrium partial pressure is just equal to x, or 0.0144 atmospheres. This is also the case for BR2. We have now determined the equilibrium partial pressures for all three species, but one important step is to check your answer. The equilibrium partial pressures should give the original value of Kp, or at least a very close value, when substituted into the Kp expression. Recall that our Kp expression has the partial pressure of I2 times the partial pressure of Br2 in the numerator, and the partial pressure of IBR squared in the denominator. We can then substitute our equilibrium partial pressures into this expression and calculate. We find that the value is 8.52 times 10 to the negative 3 as expected. In this lecture, you have seen how to calculate equilibrium concentrations or partial pressures from initial concentrations and the value of Kc. There are several important things to remember. First, we must know the initial concentrations and the value of Kc or Kp in order to calculate the equilibrium concentrations. Secondly, we begin with the ICE table and all initial concentrations that we know. 3. The changes are always a variable. The coefficient on the variable is always equal to the stoichiometric coefficient for that species. 4. We carefully solve the polynomial for the variable. Negative roots or imaginary roots are not physical and should be ignored. 5. Don't forget to use the equilibrium line of the ICE table to finish solving for the equilibrium concentrations. And lastly, always check to make sure that your equilibrium values return your Kc or Kp value. While we only worked one example in this lecture, the following 3 lectures will provide additional examples. Please be sure to watch these, and again, pause the videos as necessary to allow you to work through each problem fully.